My name is Erhan Selcuk Haciomeroglu. Today I'd like to talk about problem solving in a dynamic mathematics environment. Why did I choose problem solving as a topic of my presentation? Because problem solving is one of the most important mathematical ideas in the mathematics curriculum. I firmly believe that problem solving is the principal reason why we teach and learn mathematics. Problem solving gives us confidence, curiosity, and the ability to think and reason in unfamiliar situations. During my presentation, I am going to present a mathematical task, a problem, and then extend that problem and discuss its possible solutions in a dynamic mathematics environment. But before I do that, I'd like to talk about George Polya. George Polya was one of the greatest mathematicians of the last century, and he wrote the influential book, How to Solve It. In his book, George Polya introduced the framework or 4 phases of problem solving. This framework has been used in numerous studies, research studies, and textbooks, and he was considered the father of problem solving in the United States. And the first stage of the problem solving is understand the problem, devise a plan, carry out the plan, and look back. What makes this framework influential and important is that George Polya was trying to shift the focus of instruction from what to think to how to think. Meaning, instead of teaching students what to do or telling them what to do, we should try to teach them how to think or help them understand why they do and why they do what they do. This is the task I'd like to discuss. It's a race between father and son, a 100-meter race. A graph is presented, and your task is to write a story that matches the graph. It is important that you explain what is occurring at A, B, and C, as well as the intervals between them, meaning what is happening at A, at the beginning of the race, what is happening between A and B, who is ahead, who is behind, and what is happening at B or the intersection, and the intervals between B and C, and at the end, who won the race. These are important mathematical ideas because when graphs or mathematical ideas are presented algebraically, students often understand. However, they fail to recognize these mathematical ideas in real-life situations. I'd like to give an example. For instance, what is the importance of y-intercept? Students, if they are presented, the equation is presented algebraically, they can easily identify the slope and the y-intercept of a given equation. However, they may not recognize these mathematical ideas in a real-life situation. For instance, if you look at A, or the beginning of the race, what do 0 and 20 represent? The graph F representing the father starts at 20. It means the father was given 20-meter head start. Or if you look at the interval between A and B, students often confuse the height of the graph with the slope of the graph, meaning they look at the graphs and think that, incorrectly of course, the graph of the father is higher than the graph of the son, therefore the father is running faster than the son between A and B. And they do not understand that father and son were running the race at a constant speed. And other questions can be asked. You know, how did you determine each person's speed? Or which person was running faster? And at the end, who won the race? Or what is the importance of intersection? But today, we are not going to focus on solving this problem. I assume that you can write the equation, write the story that matches this graph, and answer the questions displayed on the screen right now. But I'd like to extend this problem and discuss possible solutions in a dynamic environment. From the graph, you can see that easily the sun has won the race with a great margin. What if I say the sun does not want to win the race? He still wants to win the race, but not with a great margin. He wants to keep it competitive. As a result, the sun decides to wait 1 second or 2 seconds or 3 seconds before he begins the race. What if I say the father was given 25-meter head start, or 30 or 40? Would that change the graph? Do you think the sun would still win the race? Let me present these problems to you. Again, the sun did not want to win the race by such a great margin, and he decides to wait 1, 2, 3, 4 or more seconds. Do you think he would still win the race? What if this father was given a 25-meter head start instead of 20, or 30-meter head start, or 40? Do you think the sun would still win the race? How can we explore all these problems in a dynamic mathematics environment? I am going to open GeoGebra. It's an open source dynamic mathematics software package. As you can see, on the y-axis we have the distance, and on the x-axis we have the time, and I did draw the graph of y equals 100 because it's a 100-meter race. So first, I'd like to sketch the graph of the functions. Y equals 10x represents the sun because he is running 10 meters per second. And the father is given, let me use f, equals 20-meter head start, and his speed is 5 meters per second. And the equation is 5x plus 20. And as you can see, the sun wins the race with a great margin. But this is not what I want to explore. I'd like the sun to wait 1, 2, 3, or 4 seconds before he begins the race, and I'd like to know if he would still win the race, and also how this changes the graph of the function. So I am going to delete the graph of these functions first, and then I am going to create sliders. For the time, I'd like to use t. Since he is going to wait 1, 2, 3, 4 or more seconds, I will use 1 as the minimum and 5 as the maximum, and the increment will be 5 right here. And for the head start, because I'd like to change the head start given to the father, for the head start, I'd like to use h, capital H, and it is going to start from, he was already given a 20-meter head start. Let's go from 20 to 50, and the increment should be 5 meters. These are arbitrary numbers. Now, I am going to enter the equations. For the sun, I'll use S equals 10, and as you remember, he still wants to win the race, but not by a great margin. So what we would like to do is, we want him to wait 1, 2 or more seconds. So what we are going to do is, we are going to subtract this from x. So I will put t so that I can control it, as you can see. Now in this situation, the sun is waiting 1 second before he begins the race. And for the father, I am going to write the equation f equals remember the equation was 5x plus 20, but I'd like to be able to change this head start. So instead of 20, I'd like to use capital H so that I can control the head start. So I'll hit that. So at this point, the father is given a 20-meter head start, and the son is going to wait 1 second before he begins the race. Who do you think is going to win the race? Let me show the label. This is the son, as you can see, and this is the father. Who wins the race? As you can see, this is the purple line, and this yellow or orange line is the son, and the son will win the race. But what if he waits 2 seconds before he begins the race? Who do you think will win the race? What if he waits 3 seconds, 4, or 5? He still wins the race. What if the father was given 25-meter head start, or 30, or 40? What if we do combinations of two things? For instance, the father was given a 30-meter head start, and the son decides to begin the race after 2 seconds. Who do you think will win the race? What if he decides to wait 3 seconds, or 4? So it's going to be a tie if the son waits 4 seconds and the father was given a 30-meter head start. So all these questions can be explored dynamically using GeoGebra, open source dynamic mathematics software. The advantage of using a dynamic mathematics software package is that when you change these values, variables, in this case, t and h, head start and the time, all the equations and the graphs will be changed simultaneously. So students will be able to see these representations and the interconnections dynamically in real time. And it is important that we present these mathematical ideas to our students in multiple representations. In other words, so as you can see on the screen, students see the graphs graphically and algebraically, because I can also present these equations on the side in the algebra window. And I can enable students or help students make the connections between algebraic and graphic representations. Thank you.